Let me help you ace your Calculus 1 final exam. I'm going to work through many problems, the first set of which are true-false questions that are tricky theoretical ones, but I will quickly move on to many calculations and applications. Number 1, true or false? If f prime of x is always positive for all x in some interval, therefore I'd also be assuming implicitly that f is differentiable on that interval, the conclusion is then f is increasing on that interval. This is true. It's a theorem. It's called the increasing function theorem. You can look it up. It's based on the mean value theorem, which will also come up in these questions. You can prove it with that. Certainly sounds true. If the slope of tangent lines are always positive, the function should be going up. Number 2, this is tricky. If f is differentiable and increasing on the interval, then f prime of x is always positive for all x in that interval. That is actually false. It sounds true. The function is differentiable, the derivative always exists, and is going up for all x in the interval. How could it be not true that f prime is always positive? That sounds true. One example that's sort of the simplest example to think about that disproves this is the x cubed function. F of x equals x cubed. Its graph looks like this. It's always increasing on any interval. However, this might seem like a minor technicality, but it is important. Its derivative at 0 is 0, right? F prime of x is 3x squared. So f prime of 0 is 0, and 0 is not greater than 0. Again, that might seem like a minor technicality, but it is actually important. It does illustrate that just because something sounds true doesn't mean it is true. What's going on here? The closer and closer you zoom in to the origin, the closer and closer the graph of the x cubed function looks like a horizontal line, though it never actually is a horizontal line. It's a very subtle point. Okay? On to number 3. If f prime of p, where p is some number, is 0, then a local maximum or local minimum must occur at x equals p. Think about that a little bit. Even think about this example. I hope it's pretty clear, based on your experience, that this is false. After all, if it were true, why in the world would we need like the first derivative test or the second derivative test? Just because you have a critical point at some point doesn't mean you have a local max or a local min there. It could be neither, like with x cubed at p equals 0. That's enough to disprove this statement. Number 4, the theorem called the extreme value theorem says that that continuous functions are the only kinds of functions that have global maxes and mins on every closed and bounded interval. Yeah, the extreme value theorem does sound somewhat like this, but the fact that I'm saying these are the only kinds of functions that have global maxes and mins makes this false. There are discontinuous functions that have global maxes and mins. I could quickly draw a graph of one. Say I have a function that starts here, goes up right to there, and then has a discontinuity, and maybe is constant over this interval, and this is a closed and bounded interval, maybe from 1 to 4 or something like that. That's a discontinuous function, but it does have a global min value, whatever the second coordinate of this point is, and it has a global max value, whatever the second coordinate of this point is. The extreme value theorem guarantees that continuous functions do have global maxes and global mins on closed and bounded intervals, but they are not the only functions that do. Number 5. The function f of x equals x to the fourth has a critical point at x equals 0. That's true, right? F prime of x is going to be 4x cubed. F prime of 0 is therefore 0. It's a critical point. But this point is neither a local max nor a local min, since the second derivative is 0 at 0 as well. F prime of x is 12x squared. F double prime of 0 is indeed 0. You might be thinking about the second derivative test. When the second derivative is positive at a critical point, the graph is concave up, so you have a local min. If the second derivative is negative at a critical point, then the graph is concave down, so you have a local max. What if the second derivative actually equals 0? Well, in general, that means no conclusion, but you could have a max or a min or neither. It depends. And if you graph x to the fourth, it looks similar to the graph of x squared, except it's a bit flatter near the origin. That flatness near the origin is enough to make the second derivative at 0 equal to 0. the graph looks pretty horizontal there, but it does have a min there, okay? When you plug in 0 and get 0, that's the smallest possible output. Plug in any other value of x, you're going to get a bigger output. It is a local min, in fact, global min at 0, so this is false. Lots of these are false so far. What about number 6? The function inverse sine of x does not satisfy the hypotheses of the mean value theorem on the interval from -1 to 1, and therefore it does not satisfy the conclusion of the mean value theorem. Okay, this is, in a sense, false in a couple of ways. It actually does satisfy the hypotheses of the mean value theorem. Now, what are the hypotheses of the mean value theorem? I'm not going to write them out, I'll just say them verbally here. You've got a function that's going to be continuous on some closed and bounded interval from a to b, and you also assume it's differentiable on the open interval from a to b, not necessarily at the endpoints. The mean value theorem will say there's some number c between a and b where f prime of c is the slope of the secant line between the extremes. Let me just illustrate with the inverse sine function. The inverse sine function, if you graph it, inverse sine of x over its domain, which is the interval from -1 to 1, the outputs end up going from negative pi over 2 to positive pi over 2, negative pi over 2 to positive pi over 2. And let's make the tick marks here maybe pi over 6 units apart or something like that. All right, let's see what we see with the graph. Here's the inverse sine function graph. It is the reflection of the sine function across the line y equals x if you made the scales on the axes the same. It is a continuous graph on the entire closed interval from -1 to 1. It is also a differentiable graph, differentiable function, on the open interval from -1 to 1. It does fail to be differentiable at the endpoints, okay? At x equals -1 and x equals +1, what happens is the slope of the tangent line goes to infinity. And that's enough to make it fail to be differentiable on the closed interval from -1 to, or at the endpoints -1 and 1. But that doesn't matter, because with the mean value theorem, it doesn't matter, your function doesn't have to be differentiable at the endpoints, okay? There is some number c where the slope of the tangent line equals the slope of the secant line. F prime of c equals the slope of the secant line. What's the secant line? It connects this point and this point. Looks about like that. There are going to actually be two values of c where the tangent line has the same kind of slope. One may be right about here. The tangent line is going to be parallel to the secant line. And one over here, symmetric, the tangent line is going to be parallel to the overall secant line. So this is false, okay? I'm making a lot of these false, but your teacher may make them trues. Number 7, the function f of x equals x cubed, or cube root of x, excuse me, does not satisfy the hypothesis of the mean value theorem on the interval from -1 to 1, and therefore it also does not satisfy the conclusion. This one turns out to be false as well, okay, but false in kind of a different way. This one was false because the inverse sine function does satisfy the hypotheses of the mean value theorem, and therefore it also does satisfy the conclusion. This one is false in a different way. It is true that it does not satisfy the hypothesis of the mean value theorem on the interval. There is a place in the, not at the endpoints, but in the middle of the interval at 0 where the slope of the tangent is infinite. If you graph the cube root function now, x to the 1/3 power, x to the 1/3 power, over the same interval, x goes from -1 to 1, and I could go -1 to 1 here. Make this 0.5 apart. Here we have a continuous graph and differentiable everywhere except in the middle of the interval, except at 0. And because that's in the middle of the interval and not the endpoints where you fail differentiability, that means this part is true actually. It does not satisfy the hypotheses of the mean value theorem. However, in spite of that fact, it still satisfies the conclusion. The secant line between these 2 points, these extremes, looks about like this. There are 2 points where the tangent line is the same slope. One may be right about there, the tangent line's got about the same slope, and one right around here where the tangent line's got the same slope as the secant line. So just because a function does not satisfy the hypotheses doesn't guarantee that this conclusion will also be failed to satisfy. I said that funny. Doesn't mean the conclusion will fail. Okay, I'll just put it that way. Okay? So I made a lot of these false. This one was true, but again, your teacher may make them true. All right, on to some applications, you might say, although this one's not, it's just sort of thinking about applications rather than doing them. Number 8, if f of t is measured in feet per second squared, it could have been meters per second squared, in other words, feet per second, and t is measured in seconds, then what are the units of the definite integral of this function from a to b? F of t is measured in feet per second squared. That means the outputs, the values of this function, are feet per second. Such units are units of acceleration, units of distance per unit of time per unit of time. If f of t is 5, for example, at some value of t, at that moment in time, the acceleration of an object moving back and forth or something is 5 feet per second. At that moment in time, the rate of change of the velocity is 5 feet per second. So it's a little confusing, but that's what it is. If you got a constant acceleration of 5 feet per second, that means every second that goes by, the velocity is increasing by 5 feet per second. So if it's 10 feet per second 1 second, it's 15 feet per second the next second, it's 20 feet per second the next second. You're speeding up faster and faster. Anyway, it's an acceleration. How do you figure out the units of the integral? What you do is you pretend. You pretend f of t and dt are being multiplied. F of t is the value of this function. It's in feet per second squared. dt is, you imagine, as being a small amount of time. And its units would be the units of t, seconds. So you would cancel one of the seconds, and the units of the integral are going to be feet per second. And that should also make sense if you think about the fact that when you integrate a rate of change, you get the total change in a function. And when you integrate an acceleration, you get the change in the velocity. Just like when you integrate a velocity, you get a change in position. Okay? That's hinting at the fundamental theorem of calculus. We'll come back to that in some later problems here. Number 9. Suppose G of V is fuel efficiency in miles per gallon of a car going at V miles per hour. Interpret the statements G of 55 equals 30 and G prime of 55 equals negative 0.5, including units, and approximate G of 57. Okay, what does this statement mean? There's no calculus there. You got to understand what this function is about. The input for this function is V, the speed of the car, 55, in this case, miles per hour. It's saying your fuel efficiency, how well your car uses fuel, is 30 miles per gallon. That's the output. When V equals 55 miles per hour, the fuel efficiency, which I'll just abbreviate there, is 30 miles per gallon. You can go 30 miles on 1 gallon when you set the cruise control at 55 miles per hour. By the way, look it up. In the United States in the 70s and early 80s, the speed limit on highways was 55 miles per hour. It was very, very slow. It was very unpleasant to go so slow. All right, but when you change your velocity, when you change your speed, the fuel efficiency can change. If you go really fast, like 80 miles an hour or something, 90 miles an hour, the fuel efficiency could be bad. It could be 20 miles per gallon or something like that. It's also probably bad if you're going really, really slow, like under 1 mile an hour or something. So it's not a constant function. It changes as a function of v. And the derivative is a measure of rate of change. G prime of 55 equals negative 0.5. What does that mean? Negative 0.5. Think about its units first. This is in, again, miles per hour. And the output is in units of G of V per unit of V. What are the units of G of V? Miles per gallon. What are the units of V? Miles per hour. The units of this are miles per gallon per mile per hour. Now, I was tempted to cancel the miles there, and technically you could say, well, I can, and the units would simplify to hours per gallon. But that's a little confusing. It's easier to understand this if you think of it as miles per gallon per mile per hour. What this is saying is, this means when you are going 55 miles per hour, when the speed is 55 miles per hour, the rate of change, the derivative, but I'll say rate of change, of fuel efficiency with respect to speed, or velocity if you prefer, is negative 0.5 miles per gallon per mile per hour. In other words, at that speed, if you increase your speed a little bit from there, from 55 to some slightly higher speed, the approximate change in your fuel efficiency would be this quantity, negative 0.5, times your change in velocity. That helps us approximate g of 57. You could say the change in g is approximately g prime of 55 times the change in v. And if v increases from 55 to 57, that's a 2-unit increase in v. This becomes negative 0.5 times 2, negative 1. And therefore, g of 57 is a little lower than 30. Your change in fuel efficiency is negative 1. Your fuel efficiency went from 30 miles per gallon down to 29 miles per gallon. It's an approximation. It's a linear approximation. So it's not necessarily exactly right. Graphically, it's using a tangent line to approximate a graph that's not necessarily straight. That's what you want to do for that problem. All right, number 10. Suppose you know that the integral of f of x from 1 to 4 is 2, the integral of f of x from 1 to 6 is negative 5, and the integral of g of x from 4 to 6 is 4. Find the value of the integral of this linear combination f of x plus 5g of x from 4 to 6. All right, properties of integrals is what we need here, abstract properties. The first thing to do is to use the fact that the integral of a linear combination like this is the integral of the first function here plus the integral of the second, and that constant 5 can be factored out. So I can write this as the integral from 4 to 6 of f of x plus the integral from 4 to 6 of 5 times g of x. The 5 can be factored out. That's called the linearity property of integrals, and it's the first thing to use. Now we know that this integral right here is 4. That's a given fact. But what is this integral? That's not given to us. We've got to figure out what that integral is. We need another abstract properties of an integral to relate these two integrals to this integral. And it's related to the fact that when you have a function, say, whose graph is always above the axis, the area under the curve between 2 points A and B can be decomposed into the sum of two areas, the area from A to C, say, plus the area from C to B. And that kind of idea applies more generally to integrals when the graph goes below the axis too. The integral from 1 to 6 of f of x can be decomposed into the sum of two integrals, the integral from 1 to 4 of f of x plus the integral from 4 to 6 of f of x. I'm using the 4 as my c because it's based on what that number is, what's given. Now use the given information. This integral here is negative 5. This is a negative 5. This integral here is 2. I need the integral from 4 to 6. That's what I'm trying to solve for. That's another motivation for using the 4 there. So now just solve for this integral by subtracting 2 from both sides. You get the integral equals negative 5 minus 2, which is negative 7. This is a negative 7. And therefore, our final answer is going to be negative 7 plus 5 times 4. That'll be negative 7 plus 20, which is 13. That'll be the final answer for this problem. In number 11, we're calculating a derivative. Ignore the point total. I forgot to delete that. Find the derivative of that crazy function there. Yikes. Well, just take it step by step. This is a sum of functions. I can differentiate each function individually and add the results. That's a linearity property of derivatives, actually. So differentiate the first function. That's a quotient. I need the quotient rule. I remember it as low d high minus high d low over the square of what's below. Low is x squared. D high means derivative of the high function. The derivative of arcsine of x is 1 over square root of 1 minus x squared. Got the 3 there, so I get 3 over square root of 1 minus x squared. Low d high minus high, 3 arcsine x. D low, derivative of x squared is 2x. So simplify a little bit, I'll get 6x, 3 times 2 is 6, arc sine x. All right, divided by the square of what's below, x squared squared is x to the 4th. Can you simplify this? Yes, you can. Do you need to? I don't require it of my students. You could factor out one factor, x to the first power to the top, cancel with one of those. You could also try to subtract fractions by getting a common denominator and that kind of stuff. I don't require my students to simplify this kind of thing. Okay, again, low d high minus high, which is arc sine x, d low, 3 times 2x is 6x, over the square of what's below. Here we have a product of two functions. I need the product rule. I also need the chain rule because both for e to the 2x and natural log of 3x, I have inside functions. The derivative of e to the 2x by the chain rule is 2e to the 2x. I take the derivative of e to the 2x by differentiating the outside function e to the x. To get e to the x, plug in the inside function 2x, and then multiply times the derivative of the inside function. The derivative of 2x is 2. That gets multiplied by ln 3x. So that's the derivative of the first times the second, plus the first function times the derivative of the second. The derivative of ln of 3x is 1 over 3x times 3, and you can cancel the 3's if you like. It's really just 1 over x. That's a little funny. The derivative of natural log of 3x is the same as the derivative of natural log of x. That's true, and it's also related to a property of logarithms, the fact that the natural log of 3x is the natural log of 3 plus the natural log of x, and the natural log of 3 is constant. So it really does give you the same derivative as the natural log of x. Anyway, so that I just used the product rule there. You could say this is d left right plus right, d left times right plus left times d right. Okay, I don't usually remember it that way, but that's the way some people remember it. On to the next term. Yikes. That's a composition of 4 functions. Most inner function is 5x. Then you take the sine, then you square, then you take the cube root. Let's make it a little simpler by realizing you could think of it as a composition of 3 functions. You could think of it as sine of 5x to the 2/3 power and differentiate that. That'll be a little easy. We really need the chain rule twice. The most outside function is raising to the 2/3 power, so I bring the 2/3 down. I need to subtract 1 from that exponent, so I get a 2/3 minus 1 is negative 1/3. And then I differentiate the inside function. I multiply times the derivative of sine of 5x, for which I need the chain rule as well, to get cosine of 5x times 5. You could simplify if you like. 2/3 times 5 would be 10/3, for example, but we'll just leave it as is. Finally, the derivative of e squared is 0, right? That's a constant. It's not e, there's no x there, so it's 0. I wrote plus 0. Of course, since you add 0, it doesn't affect anything. You don't have to write it. All right, number 12. Find the exact value of this definite integral. Integral from 0 to 1/2 of 1 over 1 plus 4x squared. This looks tricky. Now, you can use substitution to do that, and I will show you how. But you also can solve this by guessing if you've got enough experience doing antiderivatives. We know the antiderivative of 1 over 1 plus x squared is something that it's memorized to be the inverse tangent function of x plus c. You can also call that the arctangent function plus c, because arctangent and inverse tangent are the same function. This does not mean tangent of x to the negative 1 power. If you meant that, you'd write it as cotangent of x, COT. And this is a similar kind of function that we're integrating. So based on this, you might be able to guess, hopefully, and also realizing that 4x squared is the same as 2x quantity squared, that the answer should involve inverse tangent of 2x, right? Because if you took the derivative of this, you get 1 over 1 plus 2x quantity squared, just like this. And then from the chain rule, you get an extra factor of 2. So it's not quite right. But because of that extra factor of 2, we can compensate by multiplying by 1/2. There is an antiderivative of 1 over 1 plus 4x squared. I could go plus c, but I don't need to because this is a definite integral. This is going to be evaluated from 0 to 1/2. I'm really using the Fundamental Theorem of Calculus here. And what am I going to get? When I do that, I plug in the top number and get 1/2 inverse tangent of 2 times 1/2 is inverse tangent of 1. And then subtract what I get when I plug in the bottom number, 1/2 inverse tangent of 0. Inverse tangent of 1, you really should have memorized to be pi over 4 in radians. That's always assumed to be in radians here unless told otherwise. And inverse tangent of 0 you should memorize to be 0. So this simplifies to pi over 8. If you want to double check things, you can use your technology. For example, inverse tangent of 1 to confirm is pi over 4. That is the same as pi over 4 right there. And you could also double check that inverse tangent of 0 is 0. Maybe we want to check that the answer pi over 8 seems about right. So about 0.393 approximately. Let's graph this function over the interval from 0 to 1/2 and see if we get the same thing. 1 plus 4x squared is what's being graphed. Window, let's go 0 to 1/2. All right, we'll just do this. There's the graph. Let's calculate the area under the curve. Number 7 is the integral. Lower limit's 0, upper limit is 0.5. The area should be 0.3 something. I forgot exactly what. 0.393. Yeah, that looks right. Okay. 0.392699908. Double check again. 0.392699908. Yes. Okay. This is correct. On to number 13. 13 looks really hard, but at least with part A, it's actually really easy. This is really part of the fundamental theorem of calculus here. Sometimes people call it the first fundamental theorem. Sometimes they call it the second fundamental theorem. There's ambiguity in how people name the fundamental theorem of calculus parts. We're differentiating an integral where the variable for the integral is in the upper limit of the integral. The x is up there, which means you need a dummy variable down here. I'm using t. I could have used something else. This is really, really easy. It doesn't matter what the number down there is. I used a 4, I could have used a 3, I could have used a 7, I could have used a pi. As long as we're in the domain of the function here, we don't want to divide by 0, so we need to start bigger than 1 there, because ln of 1 is 0. When you differentiate the integral, it's like the derivative and the integral signs cancel, along with the dt going away as well. And this will equal then the function you were integrating. It equals the integrating function, but do not write 1 over ln of t, write 1 over ln of x. Right? The variable for this quantity here is not t. T is again called a dummy variable. It doesn't really matter what we call it. The variable for this quantity is x. The value of this integral depends on x. Different x's give you different areas under the curve and different integral values. That's the variable right there, not that. We're differentiating with respect to that variable, and therefore the answer has to be that involve that variable x. So don't write 1 over ln of t, write 1 over ln of x. Here, it's a little different because we had an x squared up there instead of an x. Doesn't matter that that's a 5 there. It could have been something else. We need the chain rule. There's an inside function here, x squared. That's what gets done first. And the outer function is essentially this function, except with a 5 instead of a 4. So the chain rule would say take the derivative of the outer function, which by the fundamental theorem of calculus is going to be 1 over ln of blank. But with the chain rule, you always plug in the inside function, which is x squared, then multiply times the derivative of that inside function, which is going to be 2x. So this derivative is 2x over ln of x squared. You can also bring that 2 down in front if you like. Property of exponents, right? This is 2x over 2 ln of x. The 2's then cancel. This simplifies to x over ln of x. Okay, kind of interesting that these derivatives are different but related to each other. Number 14, calculate a limit. The limit as x goes to 0 of ln of 1 plus x divided by 2x. Now with some limits that you calculate in calculus classes, you use factoring and canceling before you plug in, before you get a continuous function in the end, and you plug in the value that x is approaching. Sometimes you're letting x go to infinity and you need to think about end behavior. You need to multiply, do various kinds of tricks, multiplying the top and the bottom of a fraction in certain ways. Doesn't seem clear what to do here unless you know L'Hopital's rule. Yeah, that's what we want to use here. This is an indeterminate form. Both the top and the bottom are approaching 0 as x approaches 0. This is a 0 over 0 indeterminate form. Don't say indeterminate, say indeterminate form. Where the top and the bottom are both approaching 0. That means this limit could be pretty much anything. It's an indeterminate form. When that happens, you can use L'Hopital's rule. That's what I'm about to use, L'Hopital's rule. to say that this limit, if it exists, will equal this limit, a similar limit with letting x still approach 0, of a new fraction where the new numerator is the derivative of the old numerator. The derivative of natural log of 1 plus x is 1 over 1 plus x. And the new denominator is the derivative of the old denominator, 2. 2 is the derivative of 2x. This is not the quotient rule, right? No quotient rule going on here. I'm not taking the derivative of this entire fraction. I'm taking the derivative of the top and the bottom individually and making a new fraction. If this limit exists, then this limit will exist and they'll be equal to each other. That's what L'Hopital's rule says here. There's also other kinds of indeterminate forms. Infinity over infinity, 0 times infinity, things like that. I'm not doing those problems. I'm keeping it fairly simple here. Don't use L'Hopital's rule if it does not apply, and here it does not apply. This is not an infinity over infinity or 0 over 0 indeterminate form. We can just plug in 0. This is a continuous function at x equals 0. Go ahead and plug in x equals 0. Now what do we get? We get 1/2 for the final answer. If you want to double check it, you could check it by graphing. Graph ln of 1 plus x divided by 2x. Graph it for x values close to 0, negative 0.5 to positive 0.5, say. Does it look like it's approaching 1/2? Yes, it does. The scale, these tick marks are 0.5 units apart. This is a 1 up here, 0 there. This is a 1/2. It looks like it's approaching a 1/2. Something to be aware of here is technically this function is undefined at x equals 0, but that doesn't matter. There is a hole in the graph at x equals 0, a point missing. It's called a removable discontinuity. But the limit exists, it equals 1/2. And we could remove that discontinuity in a piecewise way by defining the function to equal 1/2 when x is 0. But that's not really what's going on here. Number 15 is another problem that looks really hard, but is actually really easy. Let f be continuous on a closed interval from a to b. Let n be a positive integer. Let delta x equal b minus a over n. Let xi equal a plus I times delta x. I hope this is familiar looking to you in the sense that this is the setup for definite integrals. What's the limit as n goes to infinity of this summation? What this is called a Riemann sum. F of xi times delta x represents, if your graph is above the axis at least, the area of an approximating rectangle. Technically speaking, what's called a right-hand sum because, for example, when I is 1, this is f of x1, which is a plus delta x. You're just to the right of a, the left endpoint of the interval. You're letting n go to infinity. The number of rectangles is getting higher and higher, which is equivalent to letting delta x go to 0. I also could say look at the limit as delta x goes to 0 here instead. Either way you think about it, this is the definite integral from a to b of the function. I'm applying this idea in an abstract setting, but if you had a particular function, like if you had xi quantity squared there, then the f of x would be x squared here. If you knew what a and b are, that could be more specific as well. There are lots of ways of making this more specific, but this is just a general example. Number 16 is an application. A bar of metal is cooling from 1,000 degrees Celsius to room temperature 20 degrees Celsius. The temperature, oh, there's a misspelling there, sorry. Temperature, not the temperature. H of the bar at time t, hours after it starts cooling, is given by this function here. By the way, you might have also learned about Newton's law of cooling in your calculus class, and you might be able to derive this function. I'm not doing that here. Just thinking about the basic calculus of it, and part A is not even calculus. It's find the temperature of the bar at the end of 1 hour. That's just functions, pre-calculus, plug in t equals 1. T is measured in time, in hours, excuse me. A is going to be f of 1. 20 plus 980 times e to the negative 1 power. That's the quote-unquote exact temperature, though the model's maybe not perfect. It's better to approximate it here. So 20 plus 980. We could go e to the negative 1. We could also divide by e, because raising e to the negative 1 power is the same as dividing by e. So I could do this. It looks like we get about 380.52 degrees Celsius. It is cooling down. By the way, if we plug in t equals 0 here, this function e to the 0 is 1. You get 20 plus 980, you get 1,000. So at time 0, it is 1,000, but it's cooled down now. The graph of this, by the way, is going to be an exponential decay shifted up by 20 units. Okay, the scale is going to be bad, but this kind of thing is going to approach 20 as a horizontal asymptote. Part B, find the average temperature of the bar over the first hour. Average temperature, different color here, over the first hour. That involves calculus because it involves the average value of a function. The average temperature is going to be the average value of the function. How do you find the average value? You take the integral and you divide by the length of the interval. You do 1 over b minus a times the integral of the function from a to b. In this case, we're talking about the first hour, so a is 0 and b is 1. So this becomes 1 over 1 minus 0 times the integral from 0 to 1 of this function, 20 plus 980 e to the negative t. That's our temperature function. Of course, 1 over 1 minus 0 is 1. So I just do the integral in the end anyway, but if it were a different interval, it would not just be the integral. I would have to divide by the length of the interval. The units for this are going to be units of f of t, which are degrees Celsius times time in hours, degrees Celsius times hours. That can't be the average of a temperature. I've got to divide by the hours here to make the units work out right to be degrees Celsius here. But as far as the math goes, we just do the integral. Need an antiderivative of this by the Fundamental Theorem of Calculus. I'm going to get 20t. A little tricky with an antiderivative of 980 e to the negative t. A little bit of guesswork is going to tell you that it's negative 980 e to the negative t. Okay, that takes a little bit of experience, but you can certainly check it by differentiation. This is a t here, not a plus sign. Got myself confused. So this is the same as 20t minus 980 e to the negative t evaluated from 0 to 1. Careful when I plug in 0 here, I'm not going to get 0. What do I get when I plug in 1? I get 20 minus 980 e to the negative 1. Subtract what you get when you plug in 0. The 20t when you plug in 0 is 0, but not the negative 980 e to the negative t. It's negative 980 times 1. So what do we get here in the end? Simplify, then bring the negative sign through. We get positive 980 plus 20 is 1,000. 1,000 minus 980 e to the negative 1. That's the average value, whereas the temperature was 20 plus 980 e to the negative 1. What does this end up being? 1,000 minus 980 divided by e. It's about 639.48 degrees. It did have to be certainly bigger than 380.52. Is it closer to 380.52 or 1,000? It's closer to 380.52, right? Than 1,000. You can double check that with your calculator if you like. That's because the graph is concave up. So it spends sort of most of the time down in lower values. So you should expect the average value of this function to be closer to the lower value on the time interval than it is to the higher value in the time interval. Number 17. Coal gas is produced at gas works. Pollutants are removed by scrubbers, blah, blah, blah. Following measurements are taken at the start of each month to show the rate at which pollutants are escaping in tons per month. So this is discrete data here. We don't have an underlying formula for this function, but this is a rate. You could call it maybe r of t to emphasize its rate. You also could call it little f of t, or even f prime of t to emphasize the derivative of something because it's a rate of change. The goal of the problem is first to make an overestimate or upper estimate and an underestimate, also called the lower estimate, for the total quantity of pollutants escaped during the 3 months, including units. Implicitly, okay, we are assuming it's becoming less and less efficient so that the pollutants are escaping more and more. We are assuming r of t is an increasing function here. We know when t is 0, it's 5. We know when t is 1, it's 7. We know when t is 2, it's 8. And when t is 3, it goes up a little faster again to be 10. So this is a mixture of concave down and concave up, perhaps, but it certainly is always increasing. The total quantity of pollutants that escapes is going to be the integral of its rate of change, the integral of this rate here, this function r of t here. It's going to be the area under this curve. Now again, I don't know the curve. I don't know a formula for R of t. I only know the data. But I do know R of t by assumption is going to be increasing because the scrubbers are getting less and less efficient. So an overestimate and upper estimate will be found by a right-hand sum. For each subinterval, take the right endpoint and use that to determine the height of your approximating rectangle. That'll be an overestimate. Notationally, it'll be R of 1 times delta t. Delta t in each case is 1. That's the amount of time in months between when this is measured. So R of 1 times 1 plus R of 2 times 1 plus R of 3 times 1. It's a right-hand Riemann sum. Using the data in the table, this is going to be 7 times 1 plus 8 times 1 plus 10 times 1. 7 plus 8 plus 10. That's going to be 25. Units would be tons. That's an upper or overestimate. A left-hand sum will give you a lower estimate. Areas that are too small because the function is increasing. R of 0 times 1 plus R of 1 times 1 plus R of 2 times 1. That'll be 5 plus 7 plus 8, and that will be 20 tons. That's a lower. Okay, so we made an upper estimate and an overestimate and an underestimate. I also could average these two and you get 22.5 tons if that were asked for. It's called the trapezoid rule if you did that. What we're asked for at the end here is assuming the rate at which pollutants are escaping is always increasing, which we've already said, because it's less and less efficient. How often would you need to measure the rate so the difference between the upper and lower estimates is less than 1 ton? Wow, that sounds hard. This difference is 5 tons, right? 25 minus 20. It turns out you can just use a formula. When your function is monotone, meaning always going up or always going down, always increasing or always decreasing on the interval, the difference between the upper and lower estimates, upper estimate minus lower estimate, in that situation is the absolute value of f of b minus f of a, or in our case, r of b minus r of a, times delta t. Let me go ahead and go back to r's here. R, okay? That's a true fact when your function is monotone. It can be seen and understood graphically. I'm not going to take the time to do so. A is 0, b is 3 here, so this becomes r of 3 minus r of 0 in absolute value times delta t. R of 3 is 10, r of 0 is 5. This becomes 10 minus 5, and absolute value is 5. This becomes 5 times delta t. No matter what delta t is, that's going to be the difference between the upper and lower estimates. We'd like this to be less than 1 ton. We want this to be less than 1. Just solve this inequality for delta t. Therefore, delta t must be less than 1/5, 0.2 months. That's how often it must be measured so that this happens. How many days is that? That would be like typically around 6 days, Close to once a week, okay? A little bit more often than once a week. When I was young, I wanted to write science fiction books, and my first attempt to do so was to write a book called The Gargorians. And the Gargorians were an alien race that lived on the planet Zod, pronounce that Zod, X-X-O-D-D, where their leader was named Garmar. And okay, so in honor of Garmar, on the planet Zod, the acceleration due to gravity is 6 gars per mar squared. 6 gars per mar. In the downward direction, of course, it is an ordinary kind of planet. Gar is a unit of distance and mar is a unit of time. If a human head, they like to hunt humans for sport, is thrown upward from an initial height of 2 gars above the ground with an initial velocity of 20 gars per mar, what is the maximum height in gars, of course? Okay, so what's going on here? We need to have a model for the height of this human head as a function of time. How do you derive the model? You can use the fact that the acceleration due to gravity is constant. We could say a is negative g. Should I use g? That's more for Earth, 9.8 meters per second squared. Okay, well, acceleration is negative 6 gars per mar squared. Okay, and it's a constant acceleration. We're assuming this. That's a fact about the universe. When you're near a planetary body, not too far off the surface, the acceleration due to gravity is going to be approximately constant. So that's what I'm assuming here. The velocity is going to be the integral of the acceleration. Maybe I want to use of t here, even though a was a constant. V of t is the integral of the acceleration. The integral of -6 is -6t plus c. And that c does happen to be the initial velocity. V of t is -6t plus the initial velocity. Upward velocity is 20, okay? Because when t equals 0, you got to get the initial velocity, and -6 times 0 is 0, so c has to be the same as the initial velocity. It's positive because it's going upward. They're throwing it up into the air on their planet Zod here, okay? We want to know the maximum height. This is the velocity. We will need to know when is the velocity 0, because you're going to reach the maximum height at a time when the velocity is 0. So we want to set this equal to 0 and solve for t. And you get t is 20 over 6. Units of time would be Mars. 10/3 Mars is when you reach the maximum height. A little funny that you find the time of the maximum height first. What is the height function itself? You may, in your problem similar to this, not in the planet Zod probably, be given the height function with g equal to 9.8 meters per second squared, for example. But here I'm going to find the height function. I'm going to integrate the velocity to get -3t squared plus 20t plus c, and the c has to be the initial height. Sets with the c there, that's going to be -3t squared. What is the initial height? Look at the problem again. The initial height is 2 gars above the ground, plus 2, okay? I've got the time for the maximum height. If you're given the height function, you'd have to find that by differentiating it, setting the derivative equal to 0, and solving for t, finding a critical point of h of t. The graph of h of t is going to look something like this. And this is going to be t equals 10/3 Mars. Okay, we're after the maximum height there, whatever that number is, in gars. All right, so we just need to plug in t equals 10/3 into this. H of 10/3. The -3 10/3 squared is going to be 100 over 9. Plus 20 times 10/3 is going to be 200 over 3 plus 2. Get a common, well, we get a little cancellation here. Get a common denominator of 3. We've got -100 over 3 plus 200 over 3 plus 2 is 6 over 3. So this becomes 106 over 3. And 106 is not divisible by 3. That's your answer in gars, right? Maximum height. Gars is a height. What is that approximately? 106 divided by 3 is going to be 35.3 gars is how high the head is going to go. That's going to be the second coordinate of this point approximately. Okay? We're not worrying about friction on the planet Zod. If you took into account the friction due to air friction, this is not going to be a perfect model. Number 19 is a related rates problem. Moving ladder. A 3-meter long ladder is leaning against a wall and the floor is slippery. The ladder is sliding so the bottom moves at a constant speed of 1 meter per second away from the wall. How fast is the top of the ladder moving down the wall when the bottom of the ladder is 2 meters away from the wall? Okay, related rates problem. You've got two quantities. A distance of the bottom of the ladder from the wall. Here's the wall over here. That's going to be x. That's changing over time. And another distance right there. That's the distance from the floor, down here's the floor, to the top of the ladder. That's also changing over time. That's y. What about the ladder itself? It doesn't change its length. It's sliding, but it's always 3 meters long. You want to use things like the Pythagorean theorem in this case to relate these quantities and use the fact that you're assuming these quantities depend on time to differentiate both sides to solve for the unknown rate. How fast is the top of the ladder moving down? Since we're describing it as how fast is it moving down, we'll actually take the absolute value of dy dt in the end to get a positive answer and just say that's moving down. But the Pythagorean theorem is going to imply x squared plus y squared equals 3 squared. which is 9. Assume both x and y depend on t. We're imagining this ladder moving, so they would depend on t. Assume they're nice differentiable functions of t as well. Assume, for the sake of the application, that we can differentiate both sides with respect to t. If you prefer, you could write x as x of t and y as y of t. If that's less confusing for you, go ahead and do that. It's not usually traditional to do so, but I do need the chain rule. If I differentiate x squared with respect to t, I get not 0, but 2x times dx dt, because x depends on t. If you prefer writing x of t there, you'd get 2x of t times x prime of t. That might be better for you if you do it that way. Do the same kind of thing with y. Y depends on t. Does 9 depend on t? No, 9's a constant. The ladder doesn't change its length. Its derivative is 0. What do we want? We want to know dx dt, or excuse me, dy dt. Solve this equation for dy dt. Subtract this from both sides, then divide both sides by 2y. You're going to get negative x over y, the 2's are going to cancel, times dx dt. It's only after you've done all your differentiation that you finally plug in the numbers. X is 2. The bottom of the ladder is 2 meters away from the wall at this instant in time that we're concerned about. dx dt is 1 meter per second. That's a 1. What's y? You need the Pythagorean theorem again to figure out y. We're at the moment in time when x is 2. What's y? Y is going to be the square root of 9 minus x squared. If x is 2, that's the square root of 9 minus 4, or square root of 5. That's square root of 5 here. That is dy dt in exact form. Therefore, the rate at which it's going down the wall is the absolute value of dy dt. Get rid of the negative sign, get 2 over root 5, which you could also write as 2 root 5 over 5. It doesn't matter. Units would be meters per second. And maybe we want to go ahead and approximate this just for clarity's sake. I'll just go 2 divided by square root of 5. It's about 0.894 meters per second. So the speed at which this part's going down the wall is smaller than the speed that this is going to the right, at least at this moment in time. It's sort of implicit that it's moving at a constant speed, so x is really a linear function of t. That didn't have to be the case, but it's the case we're assuming here. Anyway, at this moment in time, this is going to be the answer approximately. In number 20, we've got an implicitly defined curve in the plane. Got a cubic in x, got an x cubed term, a quartic in y, and ultimately the degree of this polynomial in 2 variables is 5, because 2 plus 3 is 5. It's crazy here. We wouldn't be able to graph this. We wouldn't be able to solve for y as a function of x very easily, at least. But we can still think about slopes of this curve. That's what we're ultimately doing, finding the equation of a tangent line. So we need a slope at a certain point, and using that in a linear approximation really to approximate the curve when x is a little bit different than 2. Is this point really on the curve? We should double check that maybe. 2 cubed is 8, times 2 is 16, minus 1 to the 4th is 15, plus this is going to be 2 squared is 4. 15 plus 4 is 19. This point does happen to be on that curve. But in part A, we want to find an equation for the tangent line to the curve at that point. We need the slope. So we need to differentiate y with respect to x. Differentiate both sides of this equation with respect to x, in fact. 2x cubed differentiates to 6x squared. What does minus y to the 4th differentiate to with respect to x? Not 0. Kind of similar to the related rates problem where we assumed x and y both depend on t. Here we're assuming y depends on x. Is that a valid assumption? It's actually not always a valid assumption. But we kind of blindly assume it's fine and just see what happens, okay? And we will see a condition under which it might not be a valid assumption. So y is really a y of x, if you prefer, or you could write it as y equals f of x if you like. We want to differentiate with respect to x, assuming y depends on x. We need the chain rule. The derivative of negative y to the 4th is not 0. It's negative 4y cubed times the derivative of the inside function with respect to x. Okay, that's the chain rule there. With the derivative of x squared times y cubed, we need the product rule and the chain rule. Derivative of the first function, x squared, is 2x times the second function. Then we have the first function, x squared times the derivative of the second with respect to x. Assume y is a function of x. Derivative of 19 is 0. Okay, if we're going to find the slope, we need to solve this for dy dx. dy dx is two terms on the left. This one has a positive sign, 3x squared, y squared. This one has a minus sign, minus 4y cubed. Bring the other terms that don't involve dy dx to the other side. Negative 6x squared minus 2xy cubed. Divide by this to solve for dy dx. I think I will also get rid of those negative signs there by switching the order of these terms after dividing. So I'll get positive 6x squared plus 2xy over, not this, but it's negative, which is 4y cubed minus 3x squared y squared. That's the general derivative in terms of both x and y. With respect to x, keep in mind y does depend on x, so it ultimately still depends on x. At the point in question, dy dx at the point 2, 1, x is 2 and y is 1, gives 6 times 2 squared is 6 times 4 is 24, plus 2 times 2 times 1 is plus 4, divided by 4 times 1 to the third is 4, minus 3 times 2 squared times 1 squared. 3 times 4 is 12. 28 over negative 8, which simplifies to negative 14 over 4, or negative 7 halves. There's the slope. We also know a point, the point 2, 1. Using point slope form, I could write y minus 1 equals negative 7 halves times x minus 2. I also could have just had the 1 on the other side right to begin with. I could write 1 minus 7 halves times x minus 2, and that's actually the easier form to use for part B. If you'd like to write this in slope-intercept form, if that's asked for, it would be y equals negative 7 halves x. Negative 7 halves times negative 2 is positive 7. 1 plus 7 is 8. Either of these answers to me is fine for part A. For part B, we're trying to estimate the y-coordinate of the point where x is 2.2. Use this tangent line approximation, linear approximation. Y of 2.2 is approximately 1 minus 3.5, 7 halves, times 2.2 minus 2. That's the change in x right there, 0.2. This is the rate of change, negative 3.5. Multiply those to get the approximate change in y, then add 1 to get the new approximate value of y. Negative 3.5 times 0.2 is going to be negative 0.7. 1 minus 0.7 is 0.3, if I've not made a mistake. Just double checking things here. 3.5 times 0.2. Yeah, and that's with the negative sign, so 1 minus that's 0.3. That's your approximate value of y when x is 2.2. Is it exactly right? I'm sure it's not. In number 20, we've got this function, and we've got 3 parts to it. Part A is to find the global maximum and minimum values of f on the interval, the closed and bounded interval from 1 to 4. This is a nice continuous and differentiable function. Got a closed and bounded interval. The extreme value theorem says global max and min values outputs will occur, will exist. Show your work, we need to take the derivative to find any critical points. So the derivative, we need the product rule. The derivative of x is 1. Then we get plus x times the derivative of e to the negative x over 2, which will be e to the negative x over 2 times negative 1/2. And for the purpose of finding critical points, we want to set this equal to 0 and solve for x. It's good to factor out any common factors. E to the negative x over 2 is a common factor, and you're left with 1 minus x over 2 in parentheses. Set this equal to 0 and solve for x. E to a power is never 0, so this must be 0. X over 2 must be 1, so x is 2 is your critical point. And that is inside the interval, so it is something we need to take into account for finding global max and min values. I'm not after local extrema here. I don't need to use the first or second derivative tests. So I can just evaluate the function at the endpoints and at the critical point to see which is the biggest output and which is the smallest output. F of the left endpoint 1 is, plug it into the original function, 1 times e to the negative 1/2, e to the negative 1/2. F of 2 is 2 times e to the negative 2 over 2, which is 2 times e to the negative 1. f of the right endpoint 4 is going to be 4 times e to the negative 4 over 2, 4 e to the negative 2. Looking at these, it's not clear which is biggest and which is smallest. Although if you graph the function, you'll see this one's actually biggest, and I think this one's going to be the smallest. Let's go ahead and graph it. So it's x times e to the negative x over 2, which is the same as negative 0.5x. Graphing it from 1 to 4, it will be positive outputs here. Let's go up to 2 just to play it safe here. Yeah, it goes up, then comes back down. That for sure is the global max at x equals 2. The global min looks like probably at x equals 4, but let's approximate these numbers anyway. So e to the negative 1/2 is about 0.6065. 2 divided by e, which is the same as 2 times e to the negative 1, is about 0.7358. 0.7358. 4 times e to the negative 2 is the same as 4 divided by e squared. Yeah, that's the smallest one, about 0.5413. So the global max value on this particular interval, if I used a different interval, of course, it would be different answers. There's your global max value in exact form, and this one is your global min value in exact form. Part B says, using part A, find numbers little m and big M so that this is true for all x. Well, your function's always got to be higher than your global min value and lower than your global max value. This part's easy. Little m is the global min value, capital M is the global max value. Little m is the global min, 4e to the negative 2. Capital M is the global max, 2e to the negative 1. Part C. Use part B to find upper and lower bounds for the value of the definite integral of this function from 1 to 4. Find numbers L and M so that this function is between them, guaranteed. Okay. By the way, the m here is going to be possibly different than the m here. It is actually going to be related because there's a theorem that says for a continuous function on an interval from a to b, if little m is the global min, then this will be true. And if capital M is the global max, then this will be true. Again, I'm using capital M in different ways here. Based on that fact, I mean, these inequalities are true even if little m is smaller than the global min and capital M is bigger than the global max. But these are your best inequalities that can be guaranteed to be true. So what I'm trying to get at here is, since the interval is from 1 to 4, b minus a is 3, 4 minus 1 is 3, I just need to multiply these by 3 to get the inequalities that I need. So little m gets multiplied by 3 to get 12 e to the negative 2 is guaranteed to be bigger than or smaller than the integral from 1 to 4 of the function x e to the negative x over 2. And multiply this one by the length of the interval, 3, you'll get 6 e to the negative 1 over there. It looks a little funny. This looks like it should be smaller than that, but it's not. This one's bigger than this one. If we'd like to approximate this, 12 times e to the negative 2. This is approximately 1.624. And this one, 6 divided by e, is about 2.207. The integral is somewhere between these two numbers. Let's go ahead and graph it. The reason this works, by the way, is that these two things give you areas of rectangles when your graph is above the axis, as this one is. So it's the same function as before, same window as before, same graph as before. What's the integral? 7, lower limit of 1, upper limit of 4. Area under the curve, it's about 2.015. Yes, that's between these two values. This is the area of a rectangle that looks approximately like this, and this one's the area of a rectangle that looks approximately like this, have a height of the minimum value on the interval. Number 22, let little f be the function whose graph is shown below. This is the graph of little f. Let capital F be an antiderivative of little f with the property that it goes through the origin. It's not graphed here. This is the graph of its derivative, little f. Find the value of x where f has a local max and the value of x where f has a local min. And we're not going to include the endpoints possibly here, but you theoretically could include the endpoints. Also find the local max and min values of capital F. Okay, this is the derivative of capital F. What does capital F itself look like? I'm assuming it goes to the origin. Think about the fact that this is the derivative. This function tells you slopes of capital F, starting out at 0, but quickly becoming negative. The graph of capital F is going to go like this. It's most negative in slope when x is 1. So I'm going to go down like this. There's going to be an inflection point there. It's going to go from concave down to concave up because its derivative goes from decreasing to increasing. There's going to be a local min right at x equals 2 here, because that's where the tangent line is going to be horizontal, a critical point for capital F, a 0 of its derivative. Then it becomes concave up. It is still concave up, but now increasing because the value of its derivative is positive. When you get to 3, there's another inflection point. Then the slope is still positive, but concave down. This slope here, this part of the graph, is steeper than the slope over here. So we're getting concave down, you might say, more than we were over there. Is it going to go above the axis or not? Actually, I think not. Let's just draw it like this here. Okay, actually, it will go above the axis slightly, sorry, at 3.5. That's going to be a local max, and then go below the axis. So there's an approximation to the graph of f. Ignore that little piece right there. Local min and local max. Local min at x equals 2. Capital F has a local min at x equals 2 and a local max at x equals 3.5. Same function here, capital F. What are the values of capital F? Local max and min values. I need the fundamental theorem of calculus. The change in capital F, delta F, over any interval from a to b can be computed by integrating its rate of change, its derivative, which is little f. So maybe it's helpful to make a table of values here. 0, 1, 2, 3, 3.5, and 4 for x. What are the values of f of x? 0 to start out with. What's the value of f of x at 1? It would be the integral of its derivative from 0 to 1, which is going to be the opposite of the area of this triangle, the negative of it. The area of a triangle is 1/2 base times height. Both the base and the height are 1. 1/2 times 1 times 1 is 1/2. But the integral is negative 1/2 because it's below the axis. Negative 0.5 is what this is. That's the change. That's the value of the integral. Therefore, the change in f is negative 0.5, so it goes down from 0 to negative 0.5. What's the change in f from 1 to 2? Capital F. It would be the integral of its derivative from 1 to 2, which is also the negative of the area of this triangle, which is also negative 0.5. So, as x increases from 1 to 2, f of x goes down by another negative. It goes down by another 0.5, from negative 0.5 to negative 1. When x goes from 2 to 3, the change in f is the integral from 2 to 3. The area of this triangle as a positive quantity. That once again has an area of 1/2. So now the value of f goes up by 1/2 to negative 0.5. And that is going to be the value of, the value of f at the local min is negative 1 here. There's the local min value. As x goes from, oh no, you know, it's not going to be above the axis. Sorry. That's a mistake. It's going to stay below the axis here. As x goes from 3 to 3.5, The output of the function does go up a little bit to your local max value, but by how much? By the area of this triangle, which is 1/2 times 1/2 times 1/4. It goes up by 1/4 from negative 0.5 to negative 0.25. That's your local max value. Finally, at x equals 4, as x increases from 3.5 to 4, the change in capital F is the integral of little f from 3.5 to 4, which is the negative of the area of this triangle, which will be negative 0.25 again. We're going to go back down to negative 0.5. So as far as answering the questions, -1 is the local min value, and negative 0.25 is the local max value. You might have a teacher that also says you can include the endpoints as local extreme points. This could be a local max, and this could be a local min, is another thing that is possible to do. Number 23 is a differential equation. Find the solution of the initial value problem. This differential equation, dy dx equals x cubed plus x squared plus x plus 1, and this initial value, y of 0, is 2. Y equals 2 when x equals 0. This sounds fancy, but it's nothing more than just doing the integral of this. Y is going to be the integral of x cubed plus x squared plus x plus 1. We'll get a plus c, and the initial value will determine the c. Solving differential equations is not always this easy, because you might have y's on the right side instead of just x's. But when you have only x's, it's really just an antiderivative problem, and you don't have to do anything fancy like separation of variables or something called integrating factors to solve it. There is the general solution. We want y to equal 2 when x equals 0. So that means c equals 2. Which means the answer is y equals 1/4 x to the 4th plus 1/3 x cubed plus 1/2 x squared plus x plus 2. That is the answer for that differential equation. Number 24. Ignore the point total. Each of the quantities below, a, b, c, d, and e, can be represented in the picture. Got a function f of x. It's this function right here. For each quantity, state whether it is a length, slope, or area. Then, using the letters in the picture, make clear exactly which length, slope, or area it represents. Part A, f of a plus h minus f of a. That's a pre-calculus kind of question. Here's x equals a, here's x equals a plus h. Those are being plugged into the function. The outputs are the second coordinates. This would be f of a right here, and this would be f of a plus h. And when you take a bigger number minus a smaller number, it is a distance between the numbers. This distance, this is a length here, of, using these letters, it would be the length of this line segment actually here. RT, if you want to emphasize that's the line segment, put a line above it. It is the change in the function as x increases from a to a plus h. Part B, f prime of a. Derivative of f at a. That's the slope of a tangent line. Here's a tangent line. This is a slope of this tangent line. Using the letters, we could write q to u. Line segment. It's the slope of that. Part C. The derivative, f prime of a, times h. H is the change in x, because x goes from a to a plus h. This is the change in x. The rate of change times the change in x. It's approximately the change in y. So it's approximately the length of r to t, though the approximation is not very good in this case, because what this really gives you is it gives you change along the tangent line. It's the length from r to u, of the line segment from r to u. That change in the tangent line is approximating the change in the function. Not very well here, but that is the idea. D, f of a times h, this height times this base. Hey, that's an area of this rectangle right there, of PQRS. And finally, state whether this quantity is represented by a length or area, and draw the length or shade the area. What does this look like? What does it look like in this form? That's the average value of f over the interval, right? Because this is the length of the interval, a plus h minus a, which simplifies to h, like that. We're dividing by that times the integral. It's an average value. As I said before, average value is really like an average height. It's a length. This is a length. It's hard to say exactly where it is in the picture, though, because it's a concave down graph. It will be closer to the highest possible value than the lowest possible value. The approximate length is going to be right about there. Okay, because that is a little closer to the higher output than the lower output because the graph is concave down. That's the height of a rectangle that over this interval right here is supposed to give you the same area as the area under the green graph. Okay? Effectively, when you do it right, this area and this area here cancel out. I didn't draw it perfectly. Okay? That's the point of that problem. We're getting close to the end, just 2 more pages. Number 25, the average value of f of x equals 6 over x squared, which is the same as 6 times x to the negative 2, over the interval from 1 to c is equal to 1. Find the value of c. So a problem-solving kind of thing. What is the average value? Well, it equals 1. It's 1 over b minus a. In this case, the interval is from 1 to c, so that's c minus 1, times the integral of the function over the interval. Function is 6x to the negative 2. I just need to solve this equation for c. 1 over c minus 1. What's the integral? Do this integral. That's the trickiest part. Antiderivative of x to the negative 2. You've got to reverse the power rule. It would be x to the negative 1 over negative 1. And the 6 can stay there. You could write it as negative 6 over x from 1 to c. Okay, double check that by differentiation. So now you plug in c first, get negative 6 over c, and subtract what you get when you plug in 1. Careful about minus signs. This becomes 6 minus 6 over c, which if you get a common denominator of c is 6c minus 6 over c, which is the same as factor out of 6. 6 times c minus 1 over c. That's what this part is. Therefore, 1 equals 1 over c minus 1 times 6 times c minus 1 over c. The c minus 1s can cancel. This simplifies to 6 over c, which implies that c is 6. There's the value of c that works. Is this right? Let's see if this seems reasonable. Go to my y equals screen, graph this function, 6 over x squared. Window from 1 to c, I got c is 6. We're wanting the average value of this to be 1. That is a decreasing function, which is biggest when x is 1. Let's go from 0 up to 6 here. Make the y scale 1 apart. There's the graph. If I make a graph of a function whose constant value is the average value, 1, is the area of that rectangle the same as the area under the curve? It's hard to say for sure, but it seems reasonable. It seems reasonable that these two areas might cancel out, okay? So I'm going to assume this is right. Number 26 is a definition of the derivative problem, not the power rule. F of x is 1 over x. Find f prime of 2. 1 over x is the same as x to the negative 1. The power rule would imply the derivative is negative x to the negative 2, negative 1 over x squared. The answer's got to be negative 1/4, but that's just a useful check. We want to use the definition of the derivative. Show your steps. F prime of 2 by definition is the limit as h goes to 0 of f of 2 plus h minus f of 2, all divided by h. The slope of a secant line, we're taking the limit of the slopes of secant lines as the change in x goes to 0, getting a slope of a tangent line by definition. Limit as h goes to 0, 1 over, use the function being 1 over x, you get 1 over 2 plus h minus 1/2 all over h. All right, just keep simplifying, don't panic here. I could subtract these fractions and also then multiply by 1 over h. I could also multiply the top and the bottom of this entire big fraction by the common denominator there of 2 times 2 plus h. I'm multiplying by, again, 2 times, in parentheses, 2 plus h on both the top and the bottom. On the bottom, it's going to give me h times 2 times 2 plus h. On the top, you get partial cancellation. The 2 plus h cancels there, leaving you with a 2. And the 2's cancel there, leaving you with a minus 2 plus h. Those 2's cancel. Negative sign going through gives you a negative h. Negative h over 2h times 2 plus h. H is canceled, leaving you with a negative 1 up top. Negative 1 over 2 times 2 plus h. Are these steps justified? Now plug in h equals 0. You get negative 1/4. What justifies these steps? Very quickly, that's the definition of the derivative. That's using the formula for the function, just algebra. This is just algebra 2, not the class algebra 2, but algebra TOO, algebra also. That's algebra. This is not just algebra there, actually. This is also based on the fact that the value of a limit is independent of what happens at h equals 0. This function is undefined. Before canceling the h's, it's undefined when h equals 0. Its graph has a hole in it at h equals 0. This function is defined at h equals 0. Why can these two limits be equal? Because they're the same function as long as h is not 0. And technically speaking, with the value of the limit, it doesn't really matter what happens at h equals 0. Though we do plug in h equals 0 at the end, because now we've got a continuous function of h at h equals 0. It's not continuous at h equals negative 2, but we don't care about negative 2. We care about close to 0, including 0. This is continuous at 0. We can now evaluate the limit by substitution. 27 is, as you look over it, a maximization or minimization problem, optimization. The volume of a circular cylinder, see the figure below? I forgot to draw it. Here's the figure. It's a can shape, circular cylinder. Of radius r and height h is area of a cylinder, pi r squared times h. And the surface area turns out to be 2 pi r squared times 2 plus 2 pi r times h. The top and the bottom are each a circle having area pi r squared. Add them together, you get 2 pi r squared. It's 2 pi r h corresponds to the side surface area of the cylinder. This is r here, this is h, which you can get by cutting it and unrolling it to get a rectangle of height h and length 2 pi r, which is the circumference of the circle. Assuming you're making soup cans and you want to find the volume, you want the volume to be fixed at 30 cubic inches. Find the dimensions of the soup can of volume 30 cubic inches with the smallest possible surface area. Verify your answer does give the smallest possible surface area. All right. You got two variables here, r and h. But this is single variable calculus. You want to get rid of one of the variables. You want to use the fact that the volume is fixed. 30 cubic inches is the fixed volume, which is pi r squared h. And you want to use that constraint, it's called, to solve, say, for h in terms of r, and then substitute that into the surface equation, or area equation, in terms of h to get just a function of r. Right? Use this constraint, solve for h, to get 30 over pi r squared. Plug that into the surface area formula in place of the h. And that's how the surface area depends on r. It can be simplified a bit. The pi's cancel. One of the r's cancels. This becomes 2 pi r squared plus 60 over r, 60 r to the negative 1. We're after minimizing this. Find the derivative. Find critical points. The derivative is 4 pi r. By the way, r has to be positive here so that you actually have a cylinder. The derivative of 60r to the negative 1 is minus 60r to the negative 2. 4 pi r minus 60 over r squared. Set this equal to 0 and solve for r. You get 4 pi r equals 60 over r squared. So r cubed is 60 over 4 is 15. 15 over r over pi, excuse me. So r looks to be the cube root of 15 over pi. Let's approximate it. 15 divided by pi to the 1/3 power. It's about 1.684. Units would be inches. We want to find the dimensions, though, so we also want the height. Use this equation here to find the height to be 30 over pi times r squared, where we substitute this value in for r. So I will go ahead and square it, then multiply by pi, then take 30 divided by that. You get about 3.368 inches for the height. So the radius is about 1.68, and the height is about 3.6368. Notice that this actually turns out to look like it's double that. I think that is right. So if I cube this, and that should be the same as 15 over pi. It is. Yeah, the radius is half the height for this to have the minimum surface area. In other words, the diameter and the height have to be the same. Interesting. Verify that it does give the smallest possible area. You can do that graphically. The graph of the surface area as a function of r looks like this. There's where the min is. You could also verify that the second derivative of s with respect to r is always positive when r is positive. Take the derivative of this, get 4 pi plus 120 r to the negative 3. And that's positive if r is positive. So the graph is always concave up when r is positive. You would have a minimum value at the point that we found, the critical point where the slope is 0. In fact, it would be a global min for all positive r. I'm not really using the second derivative test officially here, but it's similar in the sense that this is always concave up. That's got to be a global min. The last page goes back to theory. Number 28, give an example that shows why the hypothesis that the interval of optimization be a closed and bounded interval, really from a to b, is necessary in the extreme value theorem. I had a true-false question about this at the beginning. If you got a continuous function on a closed and bounded interval like this, it will have a global max or a global min. Discontinuous functions can have them too, but it's no guarantee. Why does the interval of optimization have to be a closed interval? Give one example. Here's a very simple example. F of x equals x over the open interval from a to b, say 0 to 1. Open interval from 0 to 1. It's a bounded interval, but it's not closed. It's open. We're not including the endpoints. This graph, this function, has no global max or min. There's no highest point and no lowest point. What? Isn't 1 the highest point and 0 the lowest output? No. You never reach 1. You get arbitrarily close, 0.9999999 with a finite number of 9s. Don't let the 0.9, don't let it be 0.9 repeating because that equals 1. Look it up. You never get to 1. You never get to 0. There's no global max or min values here. This is bounded. The outputs never get above 1, they never get below 0, but they never actually attain 1 or 0 in value because the interval is open. I'm not including the endpoints as part of the domain. You also can come up with examples where the interval is the entire real number line. For example, even a function like e to the x has no global max or min over the entire real number line. There's no highest point, there's no lowest point. It goes up forever and ever here. It goes down towards 0 and gets arbitrarily close to 0 forever and ever. But it never actually reaches 0, so it doesn't have a global min either. Okay, so either kind of example like this would be fine. Number 29. Give an example why the hypothesis that f be differentiable on the open interval from a to b is necessary in the mean value theorem, which I also described at the beginning. The function's got to be continuous on a closed interval from a to b, differentiable on the open interval. Then there will be a point c where this f prime of c, the slope of the tangent, equals the slope of the secant lines between the extreme points at a and b. I am assuming f is defined in the closed interval from a to b here. Simplest example here is the absolute value function. Absolute value function with a being, say, -1 and b being +1 has a graph that looks like this. And it's a necessary hypothesis because there is no tangent line that has the same slope as the secant line here when the slope is 0. If a equals -1 and b equals 1, if these are opposites of each other, then the slope of this secant line is going to be 0. But because of the corner in the graph there, the lack of differentiability at the origin, there's no tangent line with a slope of 0. They either have a slope of -1 or a slope of +1. 30. Suppose you have two functions f and g with the property that f prime of x equals g of x and g prime of x equals f of x. Show that the function h of x equals f of x squared minus g of x squared is a constant function. Suppose in addition that f of 0 is 1 and g of 0 is 0, what must this constant value of h be? We need the constant function theorem here. We're doing a proof. What's the constant function theorem say? The constant function theorem says that if you've got a differentiable function whose derivative is always 0, then the function must be constant. We're trying to show h of x is constant, so we need to take its derivative. Note that h and g, or h is differentiable for all x since f and g are. That's an implicit assumption here. That since these derivatives are equal to the function values for all x, I'm assuming they're differentiable for all x. By the chain rule, if we want to be extra careful about things, chain rule, what is h prime of x? 2 times f of x times f prime of x minus 2 times g of x times g prime of x. I'm using the chain rule there for both of these terms. Inside function here is f of x. The squaring function is the outside. Similar for this one. The derivative of difference is the difference of the derivatives. So, h prime of x, what do we do with this? Use the assumptions. If you don't use these, what are they good for? Well, you have to use what you're assuming. Replace f prime with g of x. Replace g prime with f of x. And lo and behold, we get two things that are the same, and they're being subtracted. This is 0 for all x. Therefore, by the constant function theorem, CFT, h of x equals c for all x and some constant c. And you're done with the proof. QED. What is that constant value of h? Use the fact that f of 0 is 1 and g of 0 is 0. H of 0 is going to be f of 0 squared minus g of 0 squared. 1 squared minus 0 squared is 1. That is the constant value of h. By the way, there are two particular functions that work for f and g. The cosh and sinh functions, f of x equals cosh, coh of x. It's called hyperbolic cosine. And h of x, or g of x equals sinh, sin(h) of x, hyperbolic sine, would be what f of x and g of x are. You can look it up. The last problem is to use the racetrack principle, which is a consequence of the mean value theorem, to prove that this inequality is true for all x greater than or equal to 2. Before we do the proof, let's think about the graph. 2x minus 1 has a slope of 2 and a y-intercept of -1. Looks about like this. That's a quadratic. Its graph is a parabola opening upward. Turns out its minimum value is at x equals 1, where it has a value of 2, it looks like. This is -1, 2 is about here, 3 is here, say. This parabola looks about like this. When x is 2, both of these functions have the same output. 2 times 2 minus 1 is 3. 2 squared is 4, minus 2 times 2 is 4 minus 4 is 0, plus 3 is 3. The outputs of these functions are the same at x equals 2. Here's 1. And yes, the quadratic, the parabola, is always above the linear function when x is greater than or equal to 2. But how do you do the proof? Racetrack principle, in terms of a race, say between two horses, starting at the same place at the same time, says if one horse always runs faster than the other, then the horse that always runs faster is always ahead. Pretty obvious, though, right? Think of that in terms of functions. We let f of x be 2x minus 1 and g of x be x squared minus 2x plus 3. These are supposed to represent positions of horses. 2 is supposed to be the starting time, so to speak. The quadratic one moves faster. It grows faster. G prime should always be bigger than F prime. And if that's the case, then G will always be ahead of F. F is always behind G, which means this inequality is true. Note that these functions are continuous and differentiable everywhere. Then F prime of x equals 2 for all x. F prime, and G prime of x equals 2x minus 2 for all x. And this is going to be greater than or equal to that for all x greater than or equal to 2. This is a function equal to 2 when x is 2. 2 times 2 minus 2 is 2. And it's growing. It gets bigger than 2 when x is bigger than 2. Clearly, f prime of x, which is 2, is less than or equal to 2x minus 2, which is g prime of x, for all x greater than or equal to 2. Also note, the horses have to start at the same place at the same time. F of 2 equals g of 2. They're both 3. Therefore, the racetrack principle implies that f of x is always less than or equal to g of x for all x greater than or equal to 2. But what is f of x? It's 2x minus 1. What is g of x? Is this. Therefore, we proved our inequality. Therefore, 2x minus 1 is always less than or equal to x squared minus 2x plus 3 for all x not greater than or equal to 0, but greater than or equal to 2. That was a typo. Okay? QED. We're done with the proof, and we're done with the video. Thanks for watching.